Hello everyone. Today we continue with computer system architecture course and our topic is multiplication algorithms. In the previous video we discussed addition and subtraction of numbers using sign magnitude and two's complement representation. I'll split this topic into two parts. In the first part we will discuss multiplication of fixed point binary numbers in sign magnitude representation, and in the second part we'll discuss the boot algorithm used to multiply numbers represented in sign two's complement form. Multiplication of two fixed point binary numbers in sign magnitude representation is done with paper and pencil by a process of add shift operations. We start with the least significant bit of the multiplier. If it is 1, the multiplicand is copied down, and if it is 0, zeros are copied down. For example, here we have 1, so the multiplicand is copied down. On the next one, again it is copied down, 0. Zeros are copied down, and again 0. We copy down zeros, and here 1, the multiplicand is copied down. The numbers copied down are shifted to the left by 1 position. The product is obtained by summing the numbers. If the numbers are signed, this is the sign for the first number and the sign for the second number, then the sign of the product can be obtained by exclusive OR the two sign bits, since the product is positive if the two signs are equal. For computer implementation, we are going to adjust this algorithm as follows. First, addition is performed on each stage. The second adjustment, instead of shifting the multiplicand to the left, the partial product is shifted to the right, so that the partial product and the multiplicand are in the required relative positions. And the third adjustment, when the corresponding bit of the multiplier is 0, no need to add, we just shift the result. Next, the hardware required for multiplying two signed magnitude numbers. The multiplier is stored in a Q register and it is signed in the QS flip-flop. The sequence counter is set to the number of bits in the multiplier, and after each operation it should be decremented by 1, and we stop when the sequence counter is 0. Initially, the multiplicand is stored in register B and the multiplier is stored in register Q. The sum of registers A and B forms a partial product, which is transferred to the EA register. Both the flip-flop, the partial product, and the multiplier are shifted to the right 1 position. Shift right E A Q. So the content of a flip-flop is shifted to the most significant bit in register A. The least significant bit in A is shifted to the most significant bit of Q register, and on the next stage, the least significant bit in the Q register, denoted by QN here, is inspected. If it is 1, we add the content of register B to register A and perform the shift. If, however, QN is 0, we do not need to add, we just perform the shift, and 0 is shifted to the E flip-flop on each shift operation. So according to this scenario, the rightmost flip-flop in register Q will hold the bit in the multiplier, which must be inspected next. Here, the hardware algorithm is demonstrated by means of flowchart for the multiply operation. Initially, multiplicand in the B register and multiplier in a Q. The sign bits are XORed to obtain the sign of the product. Both E flip-flop and the A register are clear to 0, and the sequence counter is set to n-1. On each iteration, we inspect the next bit in Qn, which holds the least significant bit of the multiplier. If it is 1, we add the multiplicand to A, and the result is stored in the E flip-flop and the A register. If Qn is 0, we do not add, and in both cases, we shift right the contents of the E flip-flop, A register, and the Q register. Here 0. Sequence counter is decremented by 1. If sequence counter is 0, we are done, and the product is in the A, Q registers. If it is not 0, we loop again by inspecting the next bit in the multiplier. Here we have the same example we did using paper and pencil. The multiplicand is stored in register B, the multiplier in register Q. Both register A and the flip-flop are clear to 0, and the sequence counter is set to the number of bits in the multiplier, which is 5 here. Next, we inspect the least significant bit in the multiplier. And since it is 1, we should add B to A here. And this is the first partial product. Next, we shift the E flip-flop A and the Q registers to the right 1 position. So here 0 is shifted here. All these bits are shifted to the right, and the least significant bit of A is shifted to the Q register. So after shifting, we'll have here 0, 1, 0, 1, 1. This one is shifted here, 1, 1, 0, 0, 1. Sequence counter is decremented by 1, and since it is not 0, we inspect the next bit in a Q. Since it's 1, we add B here, and the result is 0, 1, 0, 0, 0, and we have a carry 1. Now we shift right E flip-flop with A and Q registers. So here we'll have this one, and these bits are shifted to the right 1 position. Here 1, and this 0 is shifted to the Q register. And we decrement the sequence counter by 1. And since it is not 0, we examine the next bit in a Q, which is 0 now. We do not need to add in this case, but we have to shift right the contents of EAQ and decrement the sequence counter by 1. And again, since it is not 0, we inspect the next bit in a Q, and again, since it is 0, we perform the shift right without addition. So here the value after shift right. And again, we decrement the sequence counter by 1. The next bit in the multiplier now is 1. So we add B. This is the result, and shift the contents of EAQ to the right by one position. So here we have the contents after the shift right operation. We decrement the sequence counter by 1, and since it is 0, we stop. And our product is in the AQ registers. In the next video, we are going to discuss both algorithm for multiplying two signed numbers represented in 2's complement form. For today, that's all. Thank you.